Other part of the chapter, we study specific heat. Specific heat of a substance is the amount of heat required to raise the temperature of unit mass of that substance through 1 degree Celsius or 1 degree Kelvin. The units of specific heat are calorie per gram degree Celsius in CGS, kilocalorie per kilogram degree Celsius in MKS, and joule per kilogram Kelvin in SI, such that 1 calorie per gram degree Celsius is equal to 1 kilocalorie per kilogram degree Celsius. 1 calorie per gram degree Celsius is equal to 4.2 joule per kilogram Kelvin, and 1 kilocalorie per kilogram degree Celsius can be written as 4200 joule per kilogram Kelvin. Hence, the specific heat is expressed in different units. For liquids and solid, there is no appreciable change in the pressure and the volume when the temperature rise is small. So, all the heat supplied is utilized to raise the temperature of the substance. Hence, solids and liquids have only one specific heat. But in case of gases, even though the temperature change is small, there is considerable change in the pressure and volume of the gas. This means when a gas is heated, some part of the supplied heat is used to increase the volume of the gas or to do external work, and the remaining part of the supplied heat is used to increase the temperature. If volume of the gas is kept constant, all the supplied heat is used to increase the temperature. Hence, gases have two specific heats, which are specific heat at constant volume and specific heat at constant pressure. If M is mass of the gas, S is the specific heat capacity, and Q is the amount of heat supplied, and theta is the rise in temperature of the gas, the amount of heat is given by the formula Q is equal to ms theta, or specific heat is given by the formula Q upon m theta. In case of isothermal expansion, heat is given to the gas and it is allowed to expand slowly. So all the heat is utilized to do external work, that is to increase the volume. So the temperature of the gas remains constant. In such case, as theta is equal to 0, S becomes infinite. In the extremely opposite case, that is in case of adiabatic compression, a gas is suddenly compressed. As a result, its temperature increases without supply of heat. In such case, Q is 0, but theta is not 0. Hence, specific heat S becomes 0. Thus, for a gas, the specific heat changes from 0 to infinity for adiabatic compression to isothermal expansion. Hence, it is necessary to define specific heat separately for constant volume and for constant pressure condition. Specific heat at constant volume is the amount of heat required to raise the temperature of unit mass of a gas through 1 degree Celsius or 1 degree Kelvin at constant volume. Specific heat at constant pressure is the amount of heat required to raise the temperature of unit mass of a gas through 1 degree Celsius or 1 degree Kelvin at a constant pressure. These specific heats are called principal specific heats. For gases, it is convenient to specify these heats for 1 mole of gas. Such specific heats are called molar specific heats. Molar specific heat at constant volume of a gas is the amount of heat required to raise the temperature of 1 mole of a gas through 1 degree Celsius or 1 degree Kelvin at constant volume. Molar specific heat of a gas at constant pressure is the amount of heat required to raise the temperature of 1 mole of a gas through 1 degree Celsius or 1 degree Kelvin at constant pressure. If m is the molecular weight of the gas, then Cp is equal to mCp and Cv can be given as mCv. It is found that specific heat at constant pressure, that is Cp, is always greater than Cv. Why? When a gas is heated at a constant volume, no heat is wasted in increasing its volume or to do external work. Hence, all the supplied heat is used to increase the temperature of the gas. Hence, less amount of heat is required for unit rise in temperature. When a gas is heated at a constant pressure, its volume increases. Hence, part of the supplied heat is used to increase the volume or to do external work. Thus, remaining part of the supplied heat is available to increase the temperature of the gas. Thus, remaining part of the heat is going to increase the temperature less than increase in the temperature in case of constant volume. Hence, more heat is needed to raise the temperature by 1 degree Celsius. Hence, Cp is always more than Cv. If Wex is the amount of external work done by the supplied heat at constant pressure and Cv is the heat used to raise the temperature of the gas through 1 degree Celsius or 1 degree Kelvin, Cp can be given as Cp is equal to Cv plus Wex. Latent heat. In general, latent heat L of a substance is defined as the amount of heat required to change the state of unit mass of that substance at constant temperature. Means, for example, it is the heat given during the conversion of ice into water, or it is the heat given during the conversion of water into steam. In this stage, there is no rise in temperature of the ice water or the water steam combination, but the heat given is utilized to change the state. When the state is changed, intermolecular distance increases. So, the part of heat supplied during the change of state is used to do this work. This work is done against the intermolecular forces. During the change of state, there is change in volume also. So, part of heat supplied is used to do this work of change in volume also. Hence, there are two kinds of latent heats. The first one, internal latent heat. It is defined as the part of total latent heat L which is used to perform internal work against the intermolecular forces of attraction to increase the intermolecular distance. It is denoted by Li. And number two, external latent heat. It is defined as the part of total latent heat L which is used to perform external work during expansion. It is denoted by Le. Therefore, L is equal to Li plus Le. If volume of 1 mole of substance changes by dV at constant pressure P, the external latent heat Le is given by PdV. Also, the work done against the internal force or internal forces is the rise in the internal energy. Thus, Li is equal to CV dt. Hence, L can be written as sum of CV dt and PdV. If you write the equation like this, it will be in the units of work or in the mechanical units such as joule. Now, L is equal to CV dt plus PdV upon J. This is the equation in terms of heat units or calorie, where J is the mechanical equivalent of heat.